uniformly for several cohomology theories, such as Hodge cohomology and also Vital and crystalline. Or if you know prismatic. If you don't know prismatic, it's perfectly fine. So I'll do this by first. So let's fix a base scheme S. And consider the category of smooth scheme over S. And for cohomology theory, I would mean such a functor f from the opposite of this category to some category C, such that this is symmetric monoidal. And this functor is monoidal. So I will assume it satisfies Freeman's formula. And also all my categories are infinity categories. So this will be like for Hodge cohomology, this will be DS. And for example, for Vital cohomology, I will put D Vital S here. And for example, for S equals like or stuff of A modulo I, where AI is a PD pair or a prism, then here then this setting will the category here will be D of A derived completed. Okay, so I'll only use this general setting, and my my way to construct this cycle. Okay, so maybe I should first say what the cycle map is. So the cycle map here will be for Y map to X for map in this category, which is an immersion. So here it will be automatically a regular immersion since Y and X are smooth. I will say closed immersion, and it's automatically regular. So a cycle map of this will be so the natural functoriality will be fx maps to fy unrestricted. And the cycle will be the other way. So it will be fy maps to fx, but there will be some twist. We will see later what the twist is. And I think if you know the cycle map of these cohomology series in advance, then you will know what to put here. So there will be some form of take-off. Okay. So I will construct this.
Sorry, what's the category SM again?
Oh.
SM?
A smooth. The category of smooth schemes over S.
Okay, thanks.
I will assume S to be QCQS, and all schemes here will be also QCQS.
So you're speaking about Gysin morphisms or stuff like that.
Yeah. Okay, so I will construct this uniformly for this cohomology series by factoring this map. So I think I will use some other inputs. We will see later what I will use. So here.
Is there any other assumption on C, such as being stable? Or?
Right, yeah. C should be. So it should be stable and presentably. I think presentability will not be that important. Okay. So I'll construct this cycle map by factoring F. So I'll factor F through. I'll construct category following. So called MS as following Annala. Iwasa, such that this F can be factored. This F factored through this category, and so F will be a functor like this, and I will. And so F will be a functor like this, and I will construct the map here, which means I will construct a map like so. In order to construct a map from Fy to Fx, it suffices to construct a map from X to Y up to some twist. Okay. So let's construct this category and also tell you what this twist is.
So you mean the map from MS?
Yeah. So and then the contravariant functor will take this to this. Okay. So okay, so this MSS, what's this? So so this will be actually the P1 motivic spectra, the category of P1 motivic spectra, and it's so its construction will be like, so we start with smooth, and we consider its Nisnevish sheaf. So with anima as values. So this will be a stack over this S, since it's a functor from this to the infinity category of spaces. And then so this is just Nisnevish sheaf, and I will impose a condition called blow-up excision. which means let's consider like which means for any regular for any immersion like that, we can consider this blow up and the exceptional divisor. And I will impose the condition that this sheaf should take this square to a fiber square. Yeah. So like this square. So blow up excision means this square blow up yx is the fiber square. Yeah, but this is still not MSS. I will so in order to get MSS from this, the final the crucial step will be inverting the pointed P1. So maybe let's recall what a spectra is. What a spectrum is. So a spectrum, or the category of spectra, is obtained from the category of anima by consider the pointed objects, and then invert the pointed S1 in the symmetric monoidal sense, which means the category of spectra is the category of anima pointed at, like, it's the initial category under the category of pointed anima such that the pointed S1 is invertible. And here we do the similar construction. So this MS as unstable will be, I will consider the pointed object log excision. The pointed object, and then in the tensor sense, we invert pointed P1. So here, pointed just means, so in this category, there's a final object is just a sheaf of constant value of point. And a pointed object is just like the category under the point. And since P1 has a point that's fixed for infinity, it's naturally a pointed object of this. And maybe I will say the symmetric monoidal structure here is the smash structure. So the symmetric monoidal structure will be like this: x times y, x times y union x times like this. So it's like algebraic topology, and in order to take this quotient, I have to work in the category of sheaves rather than the smooth schemes themselves. Okay, so I take this and I invert this. So I take the initial category under this category such that this object is invertible. And there is a way to like somewhat explicitly describe this category, but I think it's of little use. You can see Annala Iwasa paper to see the somewhat explicit way. Okay. So finally, this does not guarantee stability, i.e. it does not guarantee like this S1 is invertible. So finally this MSS will be taken to be also invert S1. Okay. So this category is somewhat is mysterious at first sight, but we will see its use.
Does it compare to the object used by De Gliese, Szysinski, and people like that?
Sorry?
The same objects that are considered by De Gliese, Szysinski, and generalize the work of.
You mean the A1 motivic?
Yes.
Yeah. So it's more general than the A1 motivic category in the sense that like so if you cohomology factors through the A1 motivic category, then it must be A1 invariant. But this does not impose A1 invariance.
It's kind of like logarithmic A1 invariant, right?
Don't suppose it's A1.
Yeah, but I don't talk about logarithmic.
No, I know
here.
about philosophy.
Yeah, I think yeah.
Speaking, right?
Yeah, I guess so. Yeah, but I'm not familiar about logarithmic.
You can consider cohomology theories like the Pietal cohomology, that the cohomology of the affine line is not zero.
Yeah. That's what. That's why I only impose P1 invertible, but not A1 invariance. So I can use this to construct like to use this in Hodge and crystalline prismatic. Yeah. Okay. So let's see so I need to do two things. One is to factor F through this category, and the second is to construct a map like that. So the first thing is rather formal, since this is just like to factor F through this, it suffices to show that F, like to impose that F satisfies Nisnevich descent, which is automatic in many cases, and also F satisfies this blow-up excision, which means your cohomology. So like take F to be your cohomology functor. This is a fiber square, and this is satisfied in all these cases. So it's so this block excision is weaker than excision, like in the sense that like for Hodge cohomology you don't get excision, like you don't get that like a J lower star no, like you don't have such you don't have like something like this. You don't have this fiber sequence, but you still have this fiber square, since it's like a blow up, and the cohomology of the regular blow up is easy to compute, and so we can factor F through this category, and to be pointed, we just put like F, the pointed X, to be the fiber of, or it could be the fiber of fx mapping to f point. And in order for f to factor through this, it suffices for it to say the P1, the pointed P1 to be an invertible object in C, which is also satisfied in these cases.
You say that you don't have excision because you cannot do the deformation to the normal cone argument because it's not a one invariant or something like that. I don't forget.
Yeah, I will do a deformation to normal cone argument.
Yeah.
Use only this. Yeah. So.
Can you say what S1 is?
So S1 is just the space, just the anima S1.
The constant shape.
Yeah, the constant shape S1. With the constant shape with value S1. Okay. So you can see that this F P1, pointed P1 is invertible. In all these cases. Okay. So I have factored F through this category, and the other thing to do is to construct the map in this category. So I will first tell you what the twist is. This twist will be the next step to construct this thing. And okay, so first, what's the twist? So here, I will take this twist to be the Thom space of over y of the normal cone of y inside x, and this is defined as the projective. So the projective total space of the normal cone plus the trivial line bundle modulo the projective count of the projective total space of this N itself. So it's a general definition of Thom space, and I will justify it by maybe a little a small example. And so here it will be so this thing will be something invertible over y. Here I mean in MS y. So it's like so it's invertible, so it's reasonable to call it the Thom space, and also this construction will be monoidal. So this Thom space of N of E plus F will be the Thom space of E smashed with Thom space of F.
So you can ask me. Essentially, could you say what's the functor from smooth schemes over S to MS over S?
So it's the natural functor. So here smooth scheme of S maps here by unita.
We need a point as well.
Okay. So it's just like adding a point.
Because you formally at the point.
Yeah. So we have smooth S map here, and it maps to the pointed by like X map to just at any point. Yeah, since you can see that the cohomology of this is the unpointed cohomology of X. So like homologically, this makes sense. And this is unita plus, I guess, follow-up excision localization if needed.
So actually under this functor, like the image of P1 and the thing you're inverting are not the same. Because
yeah, we are not inverting the image of P1. Like that because the cohomology of P1 is not invertible. Only the pointed P1 is invertible.
And this term space is
Yeah, this is automatically pointed since the quotient is pointed by this point.
how much does that depend on?
Okay, so it only depends on this bundle. So the Thom space is it's a construction that you input a bundle. Yeah, you can see the definition here. Like once you put the same bundle, the output here is the same.
In conversation, you put line question mark. Question mark.
Yeah. Yeah, but I would say once it's oriented, like if you have a Chen class, then this only depends on the dimension, the relative dimension. Yeah, but I will not talk about the theory of the orientation. Yeah. Okay. So
Sorry, can I ask just a stupid question? So in the usual theory, if you take x times a1 and you put this somewhere in, then this a1 disappears. So is it true that if you put x times p1 in this theory, then you get the same thing, and you apply f to it, you get the same thing as f applying to x, or is it?
no, you can. Okay, so yeah, here, yeah, in A1 invariant theory, x times A1 is isomorphic to S in the category, but here it's never, since we will apply this to cohomologies and times P1 actually change the cohomology.
What does it mean to invert this p1 times thing?
So it's
Can you give
in
an
the
example?
monoidal, in symmetric monoidal sense. So it's so the definition of this will be like the initial symmetric monoidal category under this category such that the pointed P1 is invertible.
Yeah, but what principle?
I'm trying to understand this question. I mean, that's.
I think what you want to do.
It's a pointed P1. So the way to think about it is like the Rham cohomology of a P1 with logarithmic structure at infinity is trivial.
No, but you want just to take reduced homology and not homology. I mean, you want.
Sorry, what are you asking?
Why what he's trying to understand is what's the difference between inverting P1 and inverting P1 pointed?
That's because in practice the cohomology of pointed P1, which means the reduced cohomology of P1 is invertible.
Yeah, that's already cohomology.
But it's only like inverting, it's not localizing in like the A1 sense, since the cohomology of pointed P1, like the reduced cohomology of P1 it's not the same as the cohomology of a point. It's only an invertible object. So I only invert it in the sense of symmetric monoidal category.
You don't force it to be zero, you force it to be something that if you put it on it's
Yeah. So this is the definition of Thom space, and I will justify it by some example. So let's see. So let's see what this is. So you can see that this is just so first the trivial bundle. If it's trivial bundle, then it's just POY over empty set, which is the pointed POY. Maybe not empty, it's a point. So it's just a point. So actually 2 points. How should I denote this? It's Y itself. Yeah, but it's viewed as a pointed thing by adding a point. And you can see that this will be Py of O plus O over Py of O, which is exactly pointed P1. So it's actually an invertible thing over Y. And similarly, if you take a trivial bundle of Rham n, then this will be Py of O n plus 1. Yeah, and I cannot simplify it further. It's just P n plus 1 y modulo P n y. And we can see why it is. We can see roughly why it is invertible. Since actually, if you smash two, like if you consider two copies of P1, pointed P1 smashed together, then it will be P1 times P1 over P1 times infinity union with infinity times P1, and so it's like a projective plane, and you quotient out this two. And by the blow up excision, you can blow up this, and we will get a blow up of infinity P1 times P1, but you quotient out by 3, so P1 times infinity times P1. Also, finally, this exceptional divisor. Yeah, but the good news is that this is exactly blow up 2 points of P2. And the 2 points, like the exceptional divisor of these 2 points will be exactly these two lines. So you blow up this and you contract these two, and you will get P2 over P1. So you can see in this example roughly that the Thom space is actually invertible and it's momentum. And it's and you can see like it's similar to the topological construction of Thom space if you know it. So the topological construction will be the whole space. You consider the sphere bundle and you quotient out you quotient out its edge and
so these can
Yeah, it's like it's similar. Like you consider the predictive compactification and you quotient out the static part. Okay. So you can also, yeah, so I will construct a map like from X to to this thing to Y of n y over X. And you'll see, like, if you're in the topological setting.
Sorry, Longke, in the previous example, you want to have Pn over mod Pn minus 1?
Sorry?
In the previous line, it doesn't matter, but is it Pn mod Pn minus 1 rather than Pn plus 1 over?
Yeah, it's Pn, Pn of Pn minus 1. So I'll construct a map like this, and you can see that it's like in topological setting, it's just the Tom-Poincaré contraction. It's since in the topological setting, this is just you contract the part outside of the a tubular neighborhood to a point. But here in algebraic setting, is more difficult. Okay, so I'll construct this by deformation to the normal cone, which means maybe before that, let's let me introduce a proposition. We consider any, maybe just one. So for any y, or maybe I would take y to the base. Let's say consider S itself, and there's two maps from S to P1S. It's just the 0 section and the 1 section are naturally homotopy. in MSS. Okay. So it's a reminiscent of like the A1 homotopy, but here, even if P1 is only inverted, we can get this thing. So why is it? So I will consider the +1 map. So it suffices to prove the +1 map from P1 to itself. Let's omit this. It's homotopic to identity. And why is it? So we can view P1 as P of O plus O. And this +1 map is just the map. It's just the map here. Like it's just the map induced by the linear map 1, 1, 0, 1. And I need to prove that it's homotopic to identity. I will say the Annala, Hoyois, Iwasa. And so since this P1, since this P1, the pointed P1 is invertible, I can do this by like the home from P1 to P1 is the same as the home from this to itself. Yeah, and maybe I will say since the unpointed P1, the unpointed P1 is actually the pointed P1 direct sum with the point. And in this point, actually the infinity point is never moved here and here. So it suffices to prove that this +1 map viewed as a map of pointed P1 is homotopic to the identity of pointed P1. And here, since it's invertible, the home from this to itself is the same as the home after smashing this. So since this, it suffices to prove this map. So I can direct sum, or I can smash a pointed P1, and it will be like this. P2. I have proved that the smash of two pointed P1s are P2 modulo P1. Is homotopic to identity of P2 modulo P1. Okay, now it comes the magic. So this is invertible in MSS, which means so the endomorphism of an invertible object is infinity, since it's the same as the endomorphism of 1 in a symmetric modulo category, which is infinity. And this matrix is a commutative. So a commutator in an infinity algebra is identity. So we have proved this. Okay. So 0 and 1 are naturally homotopic. Since like
you take the commutation that comes from the infinity structure. You don't take anything.
No, I mean this is, so this matrix has the form A times B times A inverse times B inverse. In this endomorphism algebra. And this is infinity. So that thing must be identity.
So there is a choice of a natural.
Yeah. So you can write this.
Yeah. Okay.
I don't get the argument. I mean, where do you use that it is an infinity algebra?
Since this, maybe I only use that as E2. Yes, since it's like a commutator.
I disagree.
That's a commutativity, okay.
Yeah, but
for the
yeah.
homotopy to be
Maybe.
natural, you need an infinity structure because you need a contractible choice.
Yes.
This is specified contractible choice.
You're right. Yeah. So I will use this in the construction that works.
Sorry, could I ask? Why couldn't you have made this argument directly with P1 to P1? Because that matrix is also a commutator inside the Borel?
Is that a commutator?
But if you take you have to take upper triangular matrices because you want to preserve infinity, right?
Okay, but maybe it's not a commutator in like you want your matrix to also preserve the infinity point, the point infinity.
But that means that it's upper triangular.
Yeah, it's upper. Yeah, so is it the commutator of upper triangle matrices? If
So,
it is, then what is it?
I guess you need something like 2 to be invertible if you want it to be commutative.
No, but it's not an SL2, it's GL2.
I have 2 under you need some invertible element on the. In GL2F2, this is not a commutator. If you have characteristic 2, you might have a small problem.
Yeah. Okay,
So the goal is to construct a map like this. So to construct this, I will take this blow up here. So I let y times 0 to be inside x times p1, and I blow up this. And this, so this exceptional divisor will be will be the projective. So this is actually the projective total space of the normal cone of this inside this, which is the normal cone of y plus the trivial bundle. Okay, so so there is also another follow-up square like this. X. And this naturally includes to this square. Okay. And you can see that so I would like to construct a map from X to this thing. And this thing is just the quotient of this by this. So I can take the quotient of, I can take the cofiber of this map, since I'm working in a stable infinity category. So I take the cofiber, and this place becomes 0. So I get a fiber sequence like this. So the first term will be, so the cofiber will give me a sequence like this. I have to I'll get so I get a fiber sequence like this. And so to construct a map from X to here, it suffices to construct a map from X to here and give a non-homotopy of this composition. And usually there is a map from X to here, since you can see that the fiber over so it's the block over y times 0, so it doesn't change any other fibers. So if you take the fiber of 1 inside P1, it will be the same as X times P1. So the fiber of this is just X. So there is a map from X inside this, or more precisely X times 1 inside this. So it maps into this thing, and to give a non-homotopy of this composition, it suffices to know that proposition. Since I have quotient without x0 times 0, and the inclusion from 1 and from 0 are canonically homotopic. So I get a non-homotopy from proposition. Now I have constructed a map like this, which is the desired map. Okay. So you can see that we still have 5 minutes. So you can see that if there is some f from some cohomology theory from this thing to whatever category it is, we can apply f to here to get something like f Tom space y to fx. And this is actually some twist form of y. Like if your f has a first term class, then actually this f of tone space can be trivialized. It will be actually fy times fy twisted by the relative dimension of y over x. This is dimensional. And we'll get a Euro cycle map. Yeah. And last night I thought about like its relation to 6 functors, and I think if you have a 6 functor formalism, then so if you have a 6 functor formalism, on this smooth S, I think you can you should impose that the cohomology of Poincaré P1 is invertible, and also the blob square, like the blob square get mapped to a fiber square, and I think from this I can get a map I can get a cycle map from I lower star 1y some twist to 1x. Yes. Yeah, I think that's all I want to say.